It's hard to understand exactly what the evolutionary path of a supermassive black hole is.
Astrophysicists like Patrick Troithart are using physics to try to answer questions about the universe we live in.
Why does the Milky Way have a 4 million solar mass black hole in the center of it? Where does that come from? How did the Earth get here? How did the sun form? All of these things are just innate questions about the natural world around us.
The latest question Patrick is trying to answer:
we do not know how supermassive black holes form in the centers of galaxies. We think that an intermediate mass black hole may be the key in the evolutionary path.
So Patrick and his team are on a quest to find intermediate mass black holes.
Not only are galaxies beautiful, but all the physics that goes into it is actually very interesting as well. I'm interested in understanding how galaxies form, how they evolve, what gives them their shapes, and the underlying physics that create these galaxies. There are really two main types of galaxies that we see in the universe. There are elliptical galaxies, which essentially are giant balls of stars that have no real structure or form to them. On the other hand, spiral galaxies, the galaxies I'm interested in, they are very structured. So if you held one in your hands, it would essentially be a very flat object. Imagine looking at like a DVD or a Blu-ray disc. That's essentially the same ratio of thickness to diameter of a spiral galaxy. So all the dust, all the stars, all the gas, everything is contained within that disc. But if you rotate it to face on, then all of a sudden all the structure really pops out. You start to see spiral arms, you see the bulge, you potentially see a bar of stars running through the center of the galaxy with arms coming off the ends of it.
The bulge at the center of a spiral galaxy contains billions of stars and something else at its core.
If you zoom way into the center of that bulge, into the nucleus of that galaxy, almost every single time you're going to find something called a supermassive black hole. And these are black holes that are millions to billions of times the mass of the sun. They seem to be only found in the centers of galaxies.
So we know they're there, but remember,
we do not know how supermassive black holes form in the centers of galaxies.
There are different types of black holes. The most common ones are stellar mass black holes, and they form when the core of a massive star collapses. The mass of the star's core condenses into a smaller and smaller volume
until it basically collapses into a point, and then you get a black hole out of that.
Stellar mass black holes are relatively small, ranging between the mass of a few times the mass of the sun up to 100 times its mass. While supermassive black holes are, well, supermassive.
These range from millions to billions of times the mass of the sun. But what we don't see are the black holes in between that. If they exist, they seem to be exceedingly rare. And we think that these intermediate mass black holes may be what actually lead into these supermassive black holes.
To learn more about intermediate mass black holes, first we have to find them. And to do that, Patrick and his team are looking at the arms of spiral galaxies.
There seems to be a relationship between how tightly wrapped the spiral arms are in a galaxy and the mass of the supermassive black hole in the center. Supermassive black holes tend to have larger masses in galaxies with larger bulges, which means that they also tend to be larger in galaxies with tightly wrapped arms. So we thought, well, why don't we just measure how tightly wrapped the arms are in thousands of spiral galaxies?
Not a small task, so Patrick and his collaborators created a way for the public to help, and 8,500 people volunteered.
We have lots of images of galaxies, but they're not very high resolution images. So the contrast between where the arms in a spiral galaxy are and the region between the arms is very low. So at the time, computers had a really hard time of distinguishing between the arms and the interarm region, so it couldn't really pick out where the arms are. But people are really good at seeing patterns, and so we thought, well, why don't we just have people kind of tell us where the arms are? So the way spiralograph works is we show you an image of a galaxy. So for instance, here we have a picture of a galaxy, white on black, but I actually find it easier to see black on white. So the spiral structure actually pops out for me. So I'm going to trace this arm right here that I can see. This one's pretty prominent, so I'm going to just trace out the ridge line for the brightest part of this arm. Here's another one.
Every galaxy was traced by at least 15 volunteers, and they processed 20,000 galaxies. But when the team started to run the data through the software they built to analyze it, they ran into an issue.
We started looking at the numbers, and we realized that things weren't actually lining up. Our software assumes that things are perfectly symmetric. So the arms of a spiral galaxy are both exactly the same. They're separated by, equally from each side of the galaxy, so on and so on. That's not the case with galaxies. If you just Google like a spiral galaxy on the internet, you're going to see that very few galaxies are actually perfectly symmetric objects. Like every galaxy is really a unique snowflake. The tricky part now was disentangling all those tracings that people have given us for all the arms in a spiral galaxy.
Patrick and his collaborators developed an algorithm that would group the trace threads into individual arms. But the algorithm has to be customized to fit each galaxy.
That's actually very tedious to do, especially when you have 20,000 galaxies. So again, now we think, okay, maybe this is where people can help us with that. So we developed a new project called Spiral Graph Cluster Buster. We're looking at the clustering of these lines and having people determine whether or not it looks like the clustering is correct or not.
So what we have on the screen here is the result of tracings from spiral graph volunteers. So we're trying to group these tracings into individual arms. So obviously you can see the individual arms, but it's actually pretty difficult for a computer to actually group those things together. This is the result of the clustering of the tracings, and each individual color represents a separate arm. And so you can see the green, the yellow, and then this dark blue. So in this case, the clustering actually worked. And so this is actually a good result. So the parameters that we use in the background to do this clustering are the correct parameters for this type of galaxy, or this galaxy specifically.
In other cases, the algorithm doesn't work as well.
This is an example where the spiral structure is tightly wrapped. And you can see that there is one arm right here, and then there's another arm interior to that. And so our algorithm should actually group those tracings together into two separate arms. But in this case, the result is that all of the tracings are the same color. So it wasn't actually able to break this apart into two separate arms. It thinks everything belongs together, which is not correct. So in this case, you would actually click no.
By telling us yes or no, this worked or not, we're collecting that information with those parameters, so that way we can eventually train an AI to look at the tracing image of a galaxy, approximate what the correct parameters should be based on your yes and no votes, so that way it picks the right parameters and then correctly clusters the tracings together for the spiral arms of the galaxy.
Analyzing these galaxies brings us one step closer to understanding how supermassive black holes form.
Astronomy is no different from any other science, right? It's just everything is much further away, and it's generally stuff you can't hold on to. So you have to be a little more creative about how you try to understand what's around you.
Do you want to get involved in finding intermediate mass black holes? Visit zooniverse.org and search for Cluster Buster.